thanks everyone for coming. Thanks Mark and Marianti for organizing this. So today I'm going to talk a little bit about potential bias that arises when looking at critical windows of exposure to air pollution in children's health. And this is joint work with Matilda Chu, Leon Hugh, Bob Wright, Rosalind Wright, and Brent Kuhl. How do I do the changing? Oh, sorry. Right, so there's a lot of evidence now that air pollution is associated with various children's health outcomes and birth outcomes, including low birth rate, risk of preterm birth, rates of childhood asthma and wheeze, among other things that we'll hear about today. And so what I'm talking about today is what are the best approaches to estimate this association, and specifically, how do I identify critical windows of exposure? So by critical windows of exposure, what I'm talking about is a period in time during gestation where there's an increased association between an exposure and a future health outcome or birth outcome. Right. So on the bottom of this slide here, what you can see is for 4 mothers in a birth cohort, the mean weekly PM2.5 exposure. And of course, we get this variability over time, and that's what we're trying to exploit, is this within mother variability, so we can identify time periods. By identifying those time periods, those critical windows, we can better estimate the association with the outcome and also start to get at mechanism. And so most of the papers that have looked at this have used what we'll call trimester average exposures, and those are just the average exposure over each of the 3 trimesters. And most commonly, they're doing this with the separate trimester average approach or separate TAE model or models. And so this model here, we're just regressing the outcome on an intercept, which is mu, and then a single trimester average exposure, so a single TAE, and then various potential confounding variables. Right. And so here, when we do this, we're using 3 separate models, 1 for each trimester, and we're limiting our analysis to consider potential windows that correspond with the clinically defined trimesters. And so this is an appealing approach because it's very easy to implement as just a linear model or a generalized linear model. And it's also convenient because the pregnancies are naturally divided up into 3 trimesters. Slight alternative of this, which is less used, is to use what we'll call the joint TAE model. And so instead of fitting 3 separate models, this is just fitting a single model with all 3 trimesters included as predictor variables. So it's a joint analysis of all 3 trimester average exposures. And when doing this, we're still limiting ourselves to windows that correspond with the trimesters, but we're adjusting for exposure during the other trimesters in this model. More recently, a lot of studies have started taking a distributed lag model approach or a DLM approach. And so here, instead of using trimesters, we're using the observed exposures at every single time point. So in the example I'll give, every week during pregnancy. And so in this model, theta sub t represents the association between exposure in week t and the health outcome. And most of these are done in the constrained distributed lag model framework, where we assume the theta t's vary smoothly over time. And this can be done with natural splines, like we'll do today, Gaussian processes, Bayesian models, penalization, lots of approaches. And the idea here is we let the data do the talking and determine where the windows are instead of constraining ourselves to the trimesters. So the motivation for this work came from an analysis of the ACCESS pre-birth cohort, which is a Boston area birth cohort. And we had weekly PM2.5 exposures at each maternal residence for each week of pregnancy. And for this specific analysis that I'll show, we had 238 mother-child pairs. And so this is one example of some results using a separate TAE model and a DLM for analysis of PM2.5 and BMI Z-score. And so this is pretty typical of what the results we got are, where when we did this by girls, for girls only, we got results for the 2 models that corresponded with each other. But when we did it in the boy-only group, we got conflicting results. So you can see there, the DLM, the dashed line, shows a peak in the association during the 2nd trimester. But the separate TAE model shows the lowest association. And this happened over and over, where the 2 models sometimes would correspond, sometimes give different results. So the question is, why are they different, and which one do we believe? So we tested this with a simulation study. We used the real exposures from these 238 mother-child pairs. By using the real exposures, we ensure that we have realistic autocorrelation structure in the data, so correlation and seasonal trends of exposure. And we simulated our outcomes using a DLM model, the B-spline basis, and a Gaussian errors. and 1,000 simulated data sets. And we did this in an environment that was free from other biases. So there are no other covariates that affected the outcome. There are no other confounding variables. There are no seasonal trends in the outcome besides those that are perfectly explained by the exposure. And there's no measurement error. So this is an environment where we should be able to recover our results. So the first two scenarios, shown in the top and bottom row here, are when the window, the true window, which is shown in the dashed line, corresponds to a single trimester. So in the top row, scenario 1, the true window is the third trimester. And in the bottom row, it's the second trimester. And so what we see here is the DLM model does pretty well. It identifies the window correctly on average. The solid line is the mean over all 1,000 data sets. Its DLM slightly over smooths. The joint TAE model does very well. Where there's no association, it estimates no association is unbiased. When there is an association, it returns something that looks like the average effect over that time period, over that trimester. The separate TAE model does well only in the trimester where there is a true association. So only in the third trimester in that first one, in the second in this bottom row. The other ones, it's clearly biased, estimating a large association in the first trimester in your top left slide, and negative associations in the other trimesters. The next two scenarios, we let the window not correspond with the trimester. So in the top row, scenario 3, it spans the second and third trimester, while in the bottom row, it's the entire second half of pregnancy. Again, the DLM does really well here. The joint TAE model gets the general ordering of the trimesters correct. It identifies that the third trimester has the largest association, and the first trimester has the smallest, but it is biased for all three. The separate TAE model gives results that don't really reflect the true pattern at all. So there we estimate a large association in the first trimester when there should be none, and we're biased in the other true trimesters where there should be an association. Then here on the top row, we look at a case where there's a constant association, so there's no defined window. The DLM and the joint TAE model do really well. Well, the separate TAE model estimates that there's variable association across the pregnancy. In the sixth scenario, there's no true association. And so all three models do very well. There's no bias. So what's going on here? Well, this is all about seasonal trends in air pollution. Right? So this figure in the top left shows PM 2.5 from one Boston area monitor. And each of the horizontal bars spans one trimester for one hypothetical birth. Right? And so you can see the height of the bars, that's the trimester average exposure. And what you see here is an oscillating pattern where you get a low, high, low, or high, low, high pattern among the three trimester average exposures. And so this oscillating pattern over the whole population gives us correlation between the trimester average exposures. That's shown in the bottom for the access cohort. So we get positive association of 0.66 between the first and the third trimester average exposure, but we get negative correlation between the second trimester average exposure in both the first and the third. All right. So why does this matter? Well, for a separate TAE model, when we want to estimate the association between the first trimester average exposure model or first trimester average exposure and the outcome, we're doing it in a model that doesn't control for exposures in either the second or the third trimester. Right? But what we see here is that the third trimester is correlated with the first trimester average exposure, and the third trimester is also associated with the outcome. So this is acting like an unmeasured confounder in our model when we don't adjust for it. So by not adjusting for this, we're inducing bias in our estimate of the first trimester average exposure effect using the separate TAE model. So to recap this, the separate TAE model can result in bias estimates and often doesn't even reflect the ordering of importance of the trimesters. This bias arises due to seasonal trends that induce correlation between trimesters, which act as confounders when they aren't accounted for. The joint TAE model was sometimes biased, but generally got the overall pattern correct because you are adjusting for exposures during the entire period. The DLM model performed best overall, and there's no bias in any method when there's no true exposure effect. So there are no confounders from the other exposures. So thanks again. Thanks to my co-authors, Mark and Marianti. And there's my email if you have questions, and we'll take some at the end.